In this video, we'll discuss about the independence of random variables, an important concept in the part about distributions of functions of random variables. Before we formally start, let's look at the following. To recall, independence means that the occurrence of an event does not affect another, meaning that they must be uncorrelated. We'll learn about independence of different events. You should have known this equation. If two events A and B are independent, then the probability of event A and B occurring together equals the multiples of their individual probability. This also applies to cases where there are three or more events. Just add the corresponding events to the equation. In the case involving random variables, we can investigate the joint distribution for several independent random variables. Mathematically, nxi's are independent when the joint distribution of all xi's, where I is from 1 to n, equals the product of all individual probability density functions of each xi. In the case of the expectations of functions of the xi's equals the product of all individual expectations of functions of all xi's. If all xi's are identical, they are independent and identically distributed random variables, which we call IID random variables. A collection of IID observations can be called a random sample from a common distribution. We now look at a simple example. Consider x1, x2, and x3, which are random samples from an exponential distribution of mean 2. The PDF of the exponential distribution is fx equal to 1 over 2 times exponential power negative x over 2. The joint PDF, therefore, is fx1, x2, x3 equal to fx cubed equals to 1 over x times exponential to the power negative 3x over 2. The mean of this joint distribution equals 2 to the power 3 equals to 8. After looking at an example, we can look at other important results. Let x1 to xn be n independent random variables with respective means mu1 to mu_n and variance as sigma 1 squared to sigma n squared. Let y be the sum of ai times xi, where ai's are constants. The mean, variance, and moment generating function of y are as follows. The mean equals the sum of all ai's times mu_i's. The variance equals the sum of all ai squared times sigma I squared. The moment generating function equals the product of all moment generating functions of ai times xi. We will talk about the proof of the aforementioned results. For a case of means, it is easy to know that mu_y equals the expected value of y, which equals the expected value of the sum of ai times xi, as known from our definition. The constants can be thrown out from a parenthesis, with xi's remaining in the expected value. We can easily come to a final result, which equals the sum of ai times mu_i's. The variance case is similar, as we can eliminate the terms that I is not equal to j, since xi's are independent. It is also similar for a moment generating function case, and you may try as an exercise. Now, we'll discuss some examples involving this concept. The first one is a very simple one, which states that two independent random variables, x1 and x2, having respective means 5 and negative 6, and variances 9 and 16. Let y equals to 2x1 plus 3x2. Then the mean of y equals 2 times 5 plus 3 times negative 6 equals to negative 8. The variance of y equals 2 squared times 9 plus 3 squared times 16 equals to 180. It's a very intuitive example just to let you know about the application of the results in computation. Another example here describes the distribution of sums of independent chi-squared distribution. We can look at this theorem first. Suppose x1 to xn are independent random variables following chi-square distribution with degrees of freedom from R1 to Rn respectively. If y equals to the sum of all xi's, then the distribution of y follows a chi-square distribution with degrees of freedom summing from R1 to Rn. The proof of this theorem is as follows. Using the result mentioned in page 9, you know the moment generating function of myt equals to the product of all moment generating functions of all xi's. By independence, myt equals to the expectation of exponential to the sum of x1 to xm times t. The moment generating function of a chi-square distribution equals 1 minus 2t to the power negative r over 2. We then have myt equals to 1 minus 2t times negative summation of r1 to rn over 2. with t smaller than 1/2. From this, we see an MGF of a chi-squared distribution with degrees of freedom R1 adding to Rn. Therefore, it finishes the proof that Y follows a chi-squared distribution with degrees of freedom R1 adding to Rn. The theorem of the above example can be extended to normal distributions. This Z1 to Zn having standard normal distributions. The double equals to the sum of Z1 squared to Zn squared. Then double has a distribution of chi squared n. The result from page 15 also applies to normal distribution with any means and variances. By using the vector Z equals to x minus mu over sigma, we can transform x to a standard normal distribution, and thus using the same condition for W, where W equals to the sum of Z1 squared, W follows chi squared n. With the above theorems, we can look at another example which talks about the mean, variance, and MGF of the sample mean of samples coming from a common distribution of mean, mu, variance, sigma squared, and moment generating function mt. To recall, the sample mean x bar equals to the sum of xi squared xi's over n. The mean of x bar is sum of expected value of xi's over n, which equals the expected value of x1, and thus equals the mu. The variance of x bar equals the sum of 1 over n squared times sigma squared, which equals to sigma squared over n. The moment generating function of x bar equals the product of moment generating function of t over n, which equals MGF of t over n whole to the power n. This example shows that x bar is an estimate of the population mean mu. Due to complication, we will take it for granted at this stage and not to discuss it here. We now come to some exercise. You should try and learn to test your understanding towards the concept taught here. And it comes to the end of this tutorial.